So in this last book, I want to continue my survey of three different constructions. And so the next one I want to talk about is the Boardman-Vogt principle. So, to motivate this, let's go back to this set space of plan. So let's say that you consider an operad O with, for simplicity, just one object. And then C is some symmetric monoidal. Then I can look at the category of O algebras in C, and that actually has a symmetric monaidal structure as well, with a tensor pair just given by by two objects with algebra structures. I tensor them in C, and then that should have a tensor pair has a canonical algebra structure. Now, if I have my two algebras in B, then I can make tensor B into an algebra. I want to start the map from O n and so sigma tensor B to B. So now I'm using that I'm working with something like sets or later spaces, or I guess in general something where my operad is enriched in something Cartesian, so that I can actually take a diagonal here. I can get a map from this to the same thing. So B. And then I can use an application of the algebra structures from A and B to end up in anything C. Generally, I can make all algebras in P, say for P, let's take it to the color upright. P, just for simplicity, this works also when O is colored, but let's keep it simple and say it's still one color. This has a colored upright structure. Where again, multimorphism of algebras from one to B is given by multimorphism between the underlying objects in B. Such that I have an equation, say alpha in Taylor equation from O following square commute. So I have any copies of the first algebra and any copies the nth algebra. Now then each of the algebra structures in A1 through N gives me a map for this operation alpha, so I can apply alpha to A1, and look at A1, and so on up to N. And then so we have a multimorphism F in P from the underlying objects of A1 to A to B. Then I can apply F equal to B. But then I can also do something else and sort of reorganize this as a list of K copies of A1 through AN. Now I can apply F K times. No, I end up in K copies of B. Then I can apply the operation alpha for the algebra structure of B, and this square should commute. And so you can imagine you can do the same also if you had many objects, but it's more complicated. So in this case, for set operads, we have an operad structure on algebras. And the same thing will be true for infinity operads. And this canonical operad structure of algebras has an adjoint. This structure of algebras is adjoint to the Boardman-Vogt tensor product. Here you map an operads from O to P algebras in Q. Supposed to be equivalent to given map of operads from O tensor P into Q, that is this Boardman-Vogt tensor product. So this is not something you can just write down in a very concrete way. In sense, you can give a generators and relations construction of this. That I'm not going to talk about, but we can describe maps out of this Boardman-Vogt tensor product more concretely as labeled bifunctional. And this is something that has a very nice description within the category of operators perspective on operads. So we might as well explain this in the infinity setting. So bifunctional in the operads is equal to the square. Bifunctional of infinity operads from O and P and Q, or P and Q are infinity operads. This is a square, so here I can take O plus P, that comes down to F star plus F star, and then Q equals next to F star. And then my bifunctor is supposed to be a map like this that commutes over the smash product of final pointed sets, such that so we should have the square, and this F should have the property that it takes pairs of inert morphisms. Yeah, so then I put repetition morphisms, doing a repetition lines. Okay, so then we can show these bifunctors are represented by infinity operad of tensor P, which is this Boardman-Vogt tensor product. And moreover, we can construct independently of this definition of the Boardman-Vogt tensor product, we can construct infinity opera structures on infinity categories of algebras, as I can outline here, but we can construct infinity opera structures on algebras in P in such a way that so as many other things in this well, it involves like a right adjoint to a pole-like functor, and let me not spell it out, but we can construct this infinity opera structure algebra P such that operator maps from Q into algebra P are the same as by functors. U into P, and therefore also so we can construct this operator structure in algebras so that maps into the represented by bifunctors, and then if you believe sort of the first point here, we get that the Boardman-Vogt tensor product is adjoint to this operator structure in algebras. Then in fact, what takes more work is that we can show that this Boardman-Vogt tensor actually gives you a symmetric monoidal structure on infinity operads. So this Lurie proves this in her algebra, and this kind of a model categorical proof, I would say. Then no, that's not a proof by Barkin and Stein one more. There are excellent the Boardman-Vogt tensor product. You see, it gives you a symmetric monoidal structure. On infinity. And so the construction of Barkin-Stein one actually uses this envelope and day convolution things that I talked about in the previous lecture, since as I mentioned, you can use the smash product on finite pointed sets. You will get a tensor product on symmetric monoidal infinity categories by day convolution. And then by embedding infinity operads in symmetric monoidal infinity categories via the envelope, you can induce that the Boardman-Vogt tensor product on infinity operads in line. Okay, so
is it known by now these two tensor products by Lurie and Barkin-Stein give like the same symmetric monoidal infinity category structure on infinity categories? Because they said originally that it's not clear.
This is still not clear, unless you have an answer.
Yeah, it's not clear to me because it's not entirely clear to me what the symmetric monoidal structure is. But it's supposed to be the same. And if you use the smash product from finite pointed sets and you do categories over finite pointed sets, and then you kind of localize that structure to the ones that are operads, then that is the same. But that's which is what Lurie, I think.
I mean, the tensor products are clearly the same. The question is whether the symmetric monoidal structures are a problem, right?
Whether they're equivalent as symmetric.
Yeah. If Lurie does the thing I think he does, then there's a proof of that isn't in the list.
Yeah, I'm asking because the paper explicitly says that it is like a non-clear thing.
Yes.
So I was curious about something.
But yeah, there is no proof in that will be made.
You think there's like 553 on? He said it is not in the literature. Will it not be in literature in the future?
That is awesome. I can't prove that.
Here's the thing. So let's get back to models here. So we have the tensor product. Like, most applications you don't necessarily. It's not so often that you really care that it's a symmetric model structure. Well, anyway. So one thing we can define using this is, of course, one thing that one can define that for the moment has nothing to do with the Boardman-Vogt tensor product is the little disk Operads. En, so this is you can define it as a one object Operad in topological spaces, where this, I'm assuming most people have seen this many times before, but we take the Kähler operations to be the topological space of embeddings from k-dimensional disks in a big orbit. That's what we say it's joint embeddings. So in dimension 2, I'll look at the space, we'll say E2 of 3 will be the space of like 3 disks that is jointly embedded into a big stand. And then the composition of the Operads is given by taking one such configuration and sticking it into another one. And then yes, this is an Operad topological spaces. Classically, and then we can just or out topological spaces of infinity groupoids and extract from this and things like En. So I should say, you can also think of En of K is homotopy equivalent to the configuration space of K points in Kelvin. And then if I take n equals 1, then E1 is equivalent to the associative Operads. And also, if I define infinity to be a colimit over En to infinity via, well, I guess to get the master tree in them, I probably want to think of these as it's probably cleanest to think of them as like embeddings of cubes rather than disks, and then there's like an embedding from En to En plus 1 that just adds process things with an interval to increase the dimension by 1. So I guess cubes and cross with 1, I get out like this. So then I can talk about this infinity as a colimit of the sequence. And this requires the usual level. So from the sets. So the reason for this is basically these configuration spaces, as you increase the dimension n, the configuration spaces become more and more connected. So like if you take a colimit of them, you're eventually going to end up being contractible. Okay. So then of course we have the additivity theorem, Volkan additivity. And this form is due to Lurie. So this says I look by the En and the M and take their Boardman-Vogt tensor product, and I get En plus N. Or in particular, if it's the N operand is equivalent to the Boardman-Vogt tensor product of N copies of the associative operand. So in other words, if we think about this junction between Boardman-Vogt tensor product and algebras, we can think of an En algebra structure where we have n compatible social multiplications. So if you say it in this way here, we've described this kind of geometrically or topologically defined operand En in terms of something that is essentially a combinatorial object. We just have the social operand and tensor together n copies of it. So I guess I have time to say a little bit about application of this. So as I said, an En algebra is a structure where you have n compatible social multiplications. So if you think about, giving that kind of structure, say, in sets or in a one category, then you have the Ekman-Hilton argument, which says that if I have two compatible social multiplications on an object in a one category, and that's the same thing as giving a single mutative addition. So basically, in a one category, E2 algebras and higher are the same thing as convolutional algebras. And whereas if we look in a general infinity category, then we really do have an infinite hierarchy of different algebraic structures interpolating between E1, the associative operand, and E infinity, the commutative operand. But there is a way to go. So we can interpolate between this situation and the infinity situation by looking at En algebras in infinity categories where the mapping spaces are truncated. So in infinity category, C is an N1 category. If all of the mapping spaces are C and Y is an N-1 type for all objects X and Y. Where N-1 type means that all the homotopy groups vanish in dimensions vanish for I greater than N-1. Okay, so then we, as a corollary of the additivity theorem, well, I guess that's what this. This is really a theorem about En operation. If C is a symmetric monoidal, in the N1 category, then the K algebras in C are equivalent to mutative algebras in C if K is greater than the equivalent of 1. Okay, so this is something you can prove about EK algebras using this topological description by configuration spaces. Like the idea of the proof is basically that, giving an EK algebra, what you want to do is to map, spaces coming from the operad, which when K is large are highly connected. You're going to map those towards mapping spaces from C, which are going to be truncated. And so if you make the connectedness high enough with respect to the truncation, you can't tell the difference. But like if you're mapping into a truncated space, if the thing you map in is sufficiently highly connected, you can't tell the difference between that and a point. And so therefore, like the map from EK to the infinity will give an equivalence of categories. So as a corollary of this, together with additivity, get a version of the Bayes-Dolan stabilization hypothesis. Which has that K equally monoidal n categories. Yeah, n categories. Which I can define as, so this is supposed to be n categories with K compatible monoidal structures. So I can think of this as E1 tensor K algebras in an infinity category of n categories. These are supposed to be equivalent to symmetric monoidal categories. See what's the index if K is greater than or equal to n plus 2. The reason for this is that cat n, you apply this theorem and check that cat n is in n plus 1 value. So for example, taking n equals 1, this is saying that if I have a one category and I equip it with a bunch of compatible monoidal structures, then those will stabilize at n equals 3. Yeah, so you get monoidal categories, graded monoidal categories, and then for 3 and higher, you get symmetric monoidal categories. And then similarly for 2 categories, there are like 4 types of things you can get, which are called monoidal, graded monoidal, and then I think it's sylectic monoidal, and then symmetric monoidal. Well, okay. And then of course, you'd have to prove that my definition of a k-fold monoidal structure is the equivalent of like you'd have to prove that an EK algebra in cat n, as I defined it, actually agrees with some classical definition of a sylectic monoidal 2 category. If you really wanted to claim this theorem, but like morally, it's very true.
I think it's called Haugseng sylectic, right? The third is still.
I don't think I can claim anything here.
You have to prove that to be.
I guess the first proof of this for a version of cat n is in my paper with Geffner on enriched infinity categories. But
Geffner house.
yeah, well. Okay, so that's what I wanted to say about the Boardman-Vogt tensor. And I guess the last topic I have time for is to talk about free algebras and more generally right time extensions. Okay, so an important property, if you have some algebraic structure and you know it's described as algebras for an operad, then quite an important property that you get from having that operad description is that there is a simple formula for free algebras of that type. So again, let's go back to the classical setting of O being a one-object operad. C is symmetrical monoidal category. And it should be compatible with coordinates of groupoids. Then the formula for the free O algebra on an object X and C, namely it's described as co-product of over n goes from 0 to infinity, and On, the operations in the operad, and over sigma n given as tensor n. So what I mean by this notation and this product of sigma n is that I think about co-product of all of n many copies of x tensor n. And then I have two actions on this, one coming from commuting via the sigma n action on On, and one coming by commuting the copies of x. And so I mod out by the diagonal sigma n action. Okay. That's three algebras, and you can do something more generally. If I have any multiple operads from F and from O to P, well, I can look at a functor from P algebras in C to O algebras in C, plus its star, given by just restricting my algebra structures along F. Makes sense if we were thinking about P algebras as just maps of operads from P to C tensor, and then we're just restricting that along a map of operads. So we have this functor, this again, if C is compatible with certain polynomials, then this functor f of a star has a left adjoint no tree, and this is given by an explicit formula. So that's what I want to state in the general infinity opera setting. This F-Lower-Schräg is this operatic left arm extension construction. Okay, so to state this, I have to introduce a notation. So now I'm backing the wall of infinity operads, so I'm doing about a map of infinity operads F from O to P, and I'll hold it itself. All right, and I have an object little p and p. All right. I over little p for the final product of I over p act with so object here will be some x in O equipped with an active morphism from Operads. Okay, I guess another formally that we'll use several times already. Well, I said that's symmetric monoidal infinity category. The tensor is compatible with K in its coordinates. If the underlying infinity category C has those coordinates, and tensor product without some shared. Then we have a following theorem. Which, not so many things here is first give you Lurie on algebra. So if P is some morphism of infinite operads, C is a symmetric monoidal infinity angular compatible with elements indexed by these guys. So we'll act over P, so compatible with all elements for all elements in P. Then upper star from P algebras in C to O algebras in C. That's the left right. That's my its values can be described by namely, if I have some algebra A, and I find a trick to it, and the value along the P, I should get over O P. So an object here is X. So that's P. I'll get my alpha from my class P. What I take the coordinate of is A of O. Oh, maybe I want to do this. I think the way I'm stating the session makes more sense if P is in exactly a color in my pride, so I feel one. It's this coordinate, and then what I can do if I have so this will live or not X. So this lives in some fiber of C tensor. This is so this alpha is an active map in P and it maps to some active map N. The ones I might try to denote by pi and a projection from P to F star. And then this lives on some active map pi of alpha. And then since I have symmetric monoidal category, I can push forward this object along pi of alpha. I.e., X, X was on this, X1, that's N, that's Xi equal 1. I take the coordinate of this thing will be this is A of X1 tensor of tensor A. So then this thing exists. Say a little bit more about proofs of that in a second. but I want to first talk about the special case of free algebras. We have the following observation. If O is some infinity opera, then so it's a subcategory O inert of the inert Cartesian morphisms. So this is like this is an infinity operator with no active match, so there are no multimorphisms, and the fiber at one is like the groupoid, the infinity groupoid of colors in O. So so O inert one is the space of colors in O. And it's basically that space, but viewed as an infinity operator with no operations. So algebras in some C for O inert, you can show are equivalent to functors from O 1 4 with T. So I'm interested in doing this left-hand extension to the inclusion of O inert into O. So if we look at the inclusion O inert to O, it's supposed to be computing colimits over these categories. So O act over P, in this case, is O inert active over some X. That's just since the only active maps in O inert are equivalences, this reduces to the core of O act over X. And for convenience, I'll write that into the groupoids of act O of X. So that's the space of active morphisms to matrix X in O. So space of all multimorphisms in the operad that map to X. Well, if X is color. So then it's a special case of the theorem. We have this underlying object functor from O algebras in C to O inert algebras in C, which I can identify with functors from space of colors. C. This has a less guide. I'll call it 3O. Then if I have now X from 401 to C, then the 3O algebra of X is given at some object there's Y in O1. The colimit over all active maps Y1 through Yn. Okay, so I'm thinking here of Y in O1. So Y is the color of my operad. Then the free O algebra on X at that color is the colimit over all active maps from Y1 to Yn to Y of the tensor product of the lines. Sorry, this is the colimit over this O of Y. In particular, this is a space, so it's a colimit over a space of interlopers.
I view operatic count extension as a left adjoint internal to the infinity two category of operads if I give it a convolution structure or something.
I've never thought about that. I'm not sure.
If you give it, for instance, the point-wise structure, given by the right adjoint important stop, you need what? You need compatibility with the slice categories, like exactly this kind of like formula. Like for instance, if you're like a distributed category, like you live in this code, like this cat CC times, and all of your slice categories are sifted, then you're like fine. But otherwise, no.
Okay, so yeah, so I have this formula, and I claim that it's related to this formula. So let me try and explain that. So let's consider the case first of all. So as follows, so my operad is effective. Then I have this in the group point O of whatever, so let's say there's a single color, which I'll call star. So O of star maps to the active of Y and F star, which is now you can complete star. It's the core of active management. The one, so everything else you need active. The one, so that's just the core of the category of finite sets, which is just the property of BC and for n. And then I have this map, and then I can recover my space ON with its sigma n action from the fiber over a point in sigma n. Otherwise, in this case, this infinity two-point actual of point is 4 point over n, ON, and then you take the sigma n orbits in it. So I can compute a colimit. I can compute a colimit over this by writing it as an iterated colimit using this map to the product of the BC lines. Like if I have a functor f is defined on the point, I can write it as a colimit over optimized to sigma n, and then the colimit over the fiber at each point, which is going to be ON F. And this is this addition union. I can write, you can compose that colimit as a co-product of colimits over B sigma n, and then colimit over ON F. But if I apply this kind of decomposition to my formula over there, I get that the 3 over x at the one object, I can write as colimit over n, colimit B sigma n, and then colimit over n, and then here and x to the point and tensor together n times. And then, well, this is now a constant functor, so this thing is just like O(n) times n, and then this coordinate over b sigma n, that's the same thing as taking the orbit of a sigma n action on this thing. So, so this really does recover this original formula. And more generally, if the space of colors was not intractable but disconnected, the classical formula corresponds to not quite the left adjoint that I described, but the adjoint to positive from all algebras in C to functors in O1, 4 to C, and then to C, where I just restrict to a point in my connected space. It's the last talk of the day, so I can just go on for as long as I want, right?
Yeah, for
Another hour, I think.
like 7 more minutes.
I don't know.
I don't think you want to go
No, I don't.
because there's space, please.
Yes.
That's a very good point. So, okay. Yeah, so I just stated this there, and then I discussed the special case of free algebras. So, I wanted to say something about, well, there's a very easy, there's a case where proving this formula for the left adjoint is quite easy. I think I will just, instead of explaining it, just say it's an exercise. So, well, basically, if you think about if C is C crosses a Cartesian model, then this F-lower shriek from O algebras in C plus to OLP algebras in C plus can be computed just by an ordinary time extension by restricting ordinary left time extension from functors from O to C. C. I have just a plain ordinary left time extension of functors. I can restrict that to monads. In other words, in this case, the ordinary left time extension functor actually takes O monoids to P monoids, and therefore it gives you a left adjoint to the restriction functor given by the right formula. Yeah, so in this case, it's not so hard to actually construct the functor. So let me say something, mention that for the more general proofs. And then also, of course, the first proof is Lurie. That's like a very complicated, so simplex by simplex construction of the orthogonal extension. And then I have a proof that holds true. We use the convolution to reduce to this easy case. We use that as a proof by Norman Shaw. And I think someone mentioned there was a proof by quite recently by Putzschick and some other people.
Lines, landscapes, and fish too.
So I haven't got time to look at that, but yeah. Maybe I'll finish this by stating a few facts about infinity categories of operator algebras. What's the same fix? The tensor is symmetrically compatible with small coordinates. Just do the denominator. Okay, always a small infinity operand. So I have this junction 3O. So some things that are true. UO is conservative. And well, although C has its limits, provided C has some. And then of course UO has to preserve them since it's the right adjoint. But more interestingly, algebra of C. Well, I assume C had was compatible with all small coordinates. So I can just say immediately that algebra of C has shifted coordinates. So it has filtered coordinates and it also has simplicial coordinates, and UO preserves these. So by combining these things, you can conclude that this adjunction is actually monadic. And then you can use some like general facts about algebras or monads to conclude that in fact algebra C has all small coordinates. And if C is actually not just for complete but presentable, then so is algebra C. Okay, and then there's a whole story about how you can recover the upright O from this free algebra monad with the target being spaces. And in fact, you can characterize infinity operads as certain monads on pre-sheaves on infinity groupoids as these analytic monads. But I think I'm going to stop now. Thank you.
How is the notion of identity with index colimits related to operatic colimits in theory?
I guess I never really believed in the notion of operatic colimits because it seems kind of unnecessary to introduce. But so basically, yeah, Lurie states it in a way where the thing you take algebras in doesn't have to be symmetric monoidal. I'm not sure. I've never come across a use for that. Maybe there is something somewhere in higher algebra, but so In the case where the target is symmetric monoidal, then an operatic colimit, as Lurie defines this, is an ordinary colimit that's preserved by tensoring with objects in C. So I'm kind of building that into my assumption that the tensor product is compatible with colimits instead. So if you wanted to weaken that assumption, then you can say that these specific colimits are preserved by tensoring, and then if you wanted this to generalize to the case of the target of a general operad, it is possible to define the notion of operatic colimits in an operad. But yeah.
When we wrote a colimit over active of point as a colimit over this transform of the sigma n's and colimit over O(n). Could you explain a bit more about how this works? So why can you write a colimit over homotopy-coherence as
I guess I'm applying sort of the general fact that if I have, it is in general for vibration, but like with categories, but I get it for, let's say I have a map into B as a morphism of infinity group points. And I have some functor from E into C, some infinity category. And if I want to compute the colimit over E, well, the colimit, so this is some functor F. And the colimit over E of, why do I call everything F? This is P. So if I take the colimit over E of my function F, I can compute that in 2 steps by first taking the left Kahn extension of F along P. And then computing the colimit of that over E. And that's just the transitivity of left Kahn extension, since I'm doing the Kahn extension from E to a point by first going from E to B and then onwards to a point. And if I explain out what this is doing, this is a colimit over B. And then I do, for every B and B, I have a colimit over the fiber E at B. F for the fiber.
Yes, so the projection from ON to ON covariance is a vibration of fibers.
So yes, I'm claiming, well, then I'm also using straightening at least. So like in this case, well, no. So I start with some space ON with a sigma n action. I can view that as a pointer from E sigma n into spaces. And so I can straighten that, but then since this is a space, the straightening is just given by taking the colimit. And the colimit of this functor is the covariance. So this corresponds to the covariance of ON, mapping to B sigma n. And then the fiber, like in general, if I have a G action on a G action on some space X, then I can view that as a functor from BG into spaces, and then the colimit of that will be something that maps will be the covariant of X, mapping to BG, and the fiber, taking the fiber, I recover X, because that's my, the value of my functor at a point is X, and it has a G action, so that the fiber of this thing is X. I guess I said the same thing like 4 times, so okay.
One more question.
I was told once, maybe wrongly, that additivity and Lurie additivity were not the same thing, because they each have their definition of tensor product. I mean, that didn't know about the tensor product of Lurie, and I guess Lurie defined something and then proved that it's for his Operads, tensor product is this. Yeah, this is not a question, but are the 2 theorems really the same or related?
I mean, I guess they're somewhat related. I don't really. So I think you can define a Boardman-Vogt tensor product on like operads in simplicial sets, but it's somehow not so like right. And so you can define it, and then you can like say it's not as homotonically well behaved as one might like it is, but but then you can use that classical Boardman-Vogt tensor product and try and compute what you get if you plug in some like concrete models of EN operads. And then there are various results that if you take some specific choices of EN operad, you get some other specific EN plus M operad. So sort of it's not a so what Dunn proved was like something like this. There are other versions of this, but I think like Schwenzel and Vogt and then some others. But but given those statements, it's not clear that you get some sort of homotopical, meaningful
Can I make wrong
statements.
choices?
Sorry?
Can I make wrong choices, right?
Yeah.
EM and the tensor.
I think you can make choices where like the tensor product is always the convenient operand. And so it's yeah.
The assertion of opera tensor the assertion of opera.
Yeah, associative.
Ah, yeah.
I guess I interrupted you before you stated the question, but did I answer it or?
It wasn't the question, so you perfectly did.
Do you want to ask the question?
Probably, but thank you.
Okay.